Let's go ahead and get started for today. So we're going to continue along with what we were doing last time, which is talking about fluids. In particular, we were discussing Bernoulli's principle. Bernoulli's principle, the equation, just to review it, P1 plus 1/2 rho V1 squared plus rho GH1 is P2 plus 1/2 rho V2 squared plus rho GH2. Hold on one second. All right, sorry about that. So that was Bernoulli's equation. Remember, this is an equation of pressure. And usually this equation is used when we have a pipe system, fluids flowing through a pipe, or a system of pipes. The pipes can change size, they can change locations, go up, go down, things like this. And we usually want to determine something about the pressure in one part of the pipe or the other. And then along with this, there's a secondary equation that lets us, or that uses the relationship between the size of a pipe and the velocity of the fluid flowing through a pipe. So we know as we can, if we have water flowing through a pipe, let's say, and then we constrict the pipe, the water will speed up because the thing which is constant in a pipe system is the volume flow rate. So how much water will flow through the pipe per second is constant. No matter what you do to the pipe, you will always have that flow rate, whatever it is for that particular system, everywhere in the pipe. And so this is called continuity. It says A1 V1 equals A2 V2. Very easy. Where A is pi r squared. That is to say, you have a pipe. The pipes that we're going to talk about are cylindrical pipes. And so the area means if you were to cut the pipe into pieces, each piece has a cross-sectional area. That is, you're looking at the face of it, the opening of the pipe. The shape of the opening is, of course, a circle. And so the area of a circle is pi r squared. And so these are the two big equations we're using for this part of the discussion on fluids. And we did an example last time of a pipe system. But for that one, we didn't have the full-on every term was important. Instead, this time, we're going to work some examples. And so the first example we're going to have is a pipe system where everything is important. That is, you have every piece of Bernoulli's equation to worry about. And so the question goes like this. Water flows through a pipe, the radius, let's say 20 centimeters, with a velocity of, let's say, 30 meters per second. The pipe then raises up by 40 meters after running after running 5 meters forward, the pipe then constricts to a radius of 10 centimeters. Calculate the difference in pressure for the system. So there's our question. We have a pipe system, water flowing through the pipe, and the pipe does some stuff. First thing we want to do is go ahead and draw it out. If we don't have a picture, sometimes it's helpful to just kind of sketch what the system looks like, and that'll help us keep track of all the information. So if I were to draw this out, we have a pipe. The pipe will be moving upwards and then constricting, so it should look something like this. Here's our original pipe. Then it goes up 40 meters. Then it moves forward for 5 meters, where it then constricts to a new size. And so I would say that is pretty much what our pipe system looks like. Let's see. Plugging in the information, we know the original radius, the starting radius of the pipe, is given as 20 centimeters. So here, the radius, 1, the first radius, 20 centimeters. Centimeters is, of course, bad units. We need meters for our units. That's true in physics for just about everything, unless specified in particular. We're always going to be using meters, kilograms, seconds, things like that. So we have to convert 20 centimeters. Well, that's easy. That's just 0.2 meters. And we also know the velocity of the fluid flowing through at the beginning, V1, is 30 meters per second. Okay. Then the pipe raises up. So it was at this location, H1. It now goes up to this new location, H2. And what I know is that H2 is 40 meters above H1. Now, what I don't know is what the particular distances are. So I don't know, is H1 the ground? Or is this going from like the second floor of a building to the fourth floor of a building? I don't know that. So how do I figure out what the actual values of H1 and H2 are? Well, this is the trick. If we remember when we talk about conservation of energy in first semester physics, we found that gravitational potential energy, that's the piece of energy in a system which deals with the height of the object. As the object goes up in height, it gains potential energy, gravitational potential energy, and as it falls, it loses that potential energy. But what we said was that whenever we discuss conservation of energy, we never really care what the actual energy is. All we ever care about is how does the energy change? And so, for instance, when we talk about gravitational potential energy, you have a ball, you're holding a rock, let's say, above the ground, and then you drop the rock and it falls to the ground. And let's say it falls, 6 feet. Well, it doesn't matter if you're standing on the second floor of a building or if you're on the ground. All that matters is you were 6 feet above the end point and you ended at the end point. So you went from 6 meters up down to 0 meters up. And the fact that you may have been on the second floor doesn't affect that. And what that implies is that when you're dealing with heights like this, you don't need to know what the actual heights are, but just how they are, how they differ, or what the difference in heights is. And so what I do whenever I have a problem like this, where the pipe changes height, I choose the lowest location to be called 0 meters. That's the 0 height position. And so for this problem, H1, I'm just going to call 0. And what that does is it forces H2 for this particular problem, since the pipe raises up by 40 meters, that means whatever I chose H1 to be, H2 is 40 more than that. And so since I chose H1 to be 0, just for convenience, H2 must be 40. Now, I don't have to choose that. I can certainly choose H1 to be 10 if I want. And then if H1 is 10, H2 is 50. No big deal. The numbers will still work out. I can choose any numbers I want whatsoever. In fact, I can call H2 0, and so H1 would be negative 40. As long as the difference between H1 and H2 are what's told in the problem, which in this case happens to be 40, what values I choose doesn't really matter. And so you should always choose those values that make the problem easiest. And what would make the problem easiest here is if one of the heights were set to 0, that way one of the terms in Bernoulli's equation, when I eventually get to it, will cancel out because it'll be 0. And so the rule I always use is when the pipe system changes heights, the lowest point in the pipe system will be the 0 height location. And so that's why I call H1 0 here, and H2 then has to be 40. Now, along with that, we are also told that the pipe constricts to a new radius. So there's an R2, which is 10 centimeters. So that's 0.1. Now notice this point here, or this part of the question. After running 5 meters forward, this information is completely meaningless to us. I don't care how far, how straight the pipe system goes. I don't care if the pipe goes 150 meters forward before it goes up in the air. That stuff doesn't matter. The only things that matter for Bernoulli's equation are the actual pressure, how fast is the fluid moving, or the size of the pipe, and how high up the pipe goes. How far forward it goes, I don't need to know. So if you see information in one of these questions that deals with how far forward a pipe goes, ignore it. Don't let it confuse you. Don't think, oh, I need to use this piece of information somewhere in my calculation. You don't. It's meaningless information, and it's there purely to test whether you can find what's important and what's not important in a question. So for this example, the fact that after it goes up 40 meters, it then runs forward 5 meters before constricting, that doesn't matter. Whether constricted immediately or 5 meters later or 500 meters later plays no role whatsoever in the answer we're going to get. So we just ignore that piece of information. And so this is what we have. Pipe of a certain size eventually raises up by 40 meters and constricts to a new size. And we want to know the difference in pressure between the beginning and the end. Okay. Any questions on thinking our way through the problem, interpreting the problem? All right, well, once we have this, we could go ahead and try solving the problem. This is a Bernoulli problem. We have a pipe, fluid flowing through a pipe, and the pipe moves around, and we want to know about the pressure. Immediately, that tells you use Bernoulli's equation. So P1 plus 1/2 rho V1 squared plus rho GH1 is the same for 2. Okay. The next step I usually do is I figure out from the information given, are there any terms here that I don't need to worry about, that I can cancel out? And the way I determine that is I say, well, does the pipe change size? If the pipe does not change size, then I know the velocity won't change. And if the velocity doesn't change, then I could just cancel out the terms that have velocity in it. In this case, however, the pipe does constrict, so I have to keep those terms. Another thing to look at, does the pipe change height? Does it go up or go down or anything like that, or does it just go straight the whole time? If it just goes straight, if it never rises up or falls down, then I could just cancel out the height terms because they would not be important. The height 1 is the same as height 2, so the terms would cancel out. In this case, of course, the pipe does raise up by 40 meters, so I have to keep the terms with height in. So there's nothing in this particular example that it will allow me to cancel out any particular term. I have to keep them all. Well, okay, no big deal. I just have to keep them all. That's the way it is. Next thing I do is I say, okay, what is it I'm looking for? I want the difference in pressure. And the difference in pressure means delta P, for our purposes, is P2 minus P1. What's the pressure at the end minus what was the pressure at the beginning? That's the difference in pressure. So I want to take Bernoulli's equation as it's written here and rearrange it so that on one side of the equation, I have P2 minus P1, and on the other side of the equation is everything else. So that's what I'll do. I look at Bernoulli, I say, okay, P2 is there on the right side, so I want to take P1 and I want to move it over to the right. Well, when I do that, of course, it becomes negative. So I have P2 minus P1 on one side. Now, of course, what that means is everything else, all of this stuff over here on the right, I have to move it over to the left side. And of course, when you do that, those things become negative, but that's fine. So if I write what's on the other side of the equation, we have 1/2 rho V1 squared. And then I'm subtracting over the 2 term, so it's minus 1/2 rho V2 squared. And then I have the height term, rho GH1. And then the rho GH2 term I brought over to the other side, so he became negative minus rho GH2. And so now that's what Bernoulli's equation looks like after I rearranged it. I took Bernoulli, moved the terms around so that on one side I have P2 minus P1 and everything else is on the other side. And that's what it becomes. And at this point, all I have to do is plug in all my numbers. I say, do I know everything to be able to solve this? That is to say, the left side is what I want. So this thing here, that is delta P. That's what I want. So I need to plug everything in on the right side. Do I know all these numbers? Well, let's look. Rho, of course, density of water, that's 1,000. So that's something I know. Density is 1,000. V1, I know V1, that's given, it's 30. V2, I don't know V2. I'm not given the speed of the fluid in the second location after it is constricted. So in order for me to solve this problem, I first have to calculate what V2 is. So let's leave Bernoulli alone. And let's move on to the side and calculate separately what will be V2. And of course, to do it, we have only one other equation to use, and that's continuity. So that's A1V1 is A2V2. Of course, what I'm looking for is V2. So I solve this for V2 equals A1 over A2 times V1. All right, plugging my numbers in. A1, that's pi times R1 squared. Well, what was R1? R1 was given as 0.2 meters. So pi times 0.2 squared. That's A1. Divided by A2 is pi times R2 squared. And R2 is given as 0.1. So 0.1 squared. So there's A1 over A2, and now I multiply it by the original velocity, which of course was given as 30. And now I have a little equation that allows me to calculate the velocity in the second part of the pipe. So when I do that, I plug everything in, notice the pi's will cancel out. The pi's will always cancel out when you do this calculation, which is nice. But if you don't cancel them out, when you plug everything in, it all works out. I get the new velocity is 120 meters per second. Now, before I use this, I have to ask myself, does it seem okay? You know, I don't want to use a number that I know is definitely wrong in my calculation. So I just want to take a couple of seconds to look at the answer and say, can I tell for sure whether it's right or wrong? How do I do it? Well, I say, originally the speed of the fluid was 30. I've then constricted the pipe. So if I constrict the pipe, do I expect the velocity to go up or do I expect it to go down? And of course, the answer is, the way I remember the answer is the whole example of putting your thumb in the end of a hose. When you do that, you constrict the opening of the pipe, the hose, and the water shoots out further because the water shoots out faster. When you constrict a pipe, the fluid velocity goes up. When you enlarge a pipe, the fluid velocity goes down. Here, I had a pipe, I constricted it, so I expect the new velocity to be bigger than the original velocity. What did I find? I found the new velocity to be 120, the original was 30. It is bigger, so it seems okay to me. Now, that's not a guarantee that it's right. Obviously, I could have made a mistake in my calculation, plugging it into my calculator or something like that, but at least when I look at it, I don't see something that's obviously wrong. If I got 20 as my answer, then I know there's something wrong because the velocity shouldn't have slowed down, it should have sped up. And so I could go back and look and check my calculation, make sure everything's okay. Here I get a bigger velocity. I expect it to be bigger, so I can be confident with it. And I move on to finishing up my problem. Now that I know what V2 is, I could go ahead and solve Bernoulli. P2 minus P1 is 1/2 rho, which is 1,000, times V1 squared, 30 squared, minus 1/2 times 1,000, times V2 squared, which is 120 squared. Then I have rho GH1, which is 1,000, times 9.8 times H1, which is 0. Remember, I chose the lowest position to be 0. So that term just becomes 0. That's nice. I could just forget it. And then rho GH2, so he's minus 1,000 times 9.8 times H2, which is 40 above the ground level. And there we go. There's all the numbers plugged into my equation. And so with this, all I have to do is plug everything in my calculator. Let's see. What do I get? 1,000 times 9.8 times 40. I get that P2 minus P1, that is the difference in pressure, is minus 7142000, or, of course, scientific notation is a lot prettier, minus 7.14 times 10 to the 1, 2, 3, 4, 5, 6 pascals. Notice the answer is negative. Is it okay to get a negative answer? Well, yeah, it's okay. All a negative answer means, remember, what I'm solving for here is the difference in pressure. So if I get a negative answer, that means the new pressure is blah, 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 less than the original pressure. So whatever the original pressure was in my pipe, because I've gone up 40 meters and I've constricted my pipe, the new pressure in the fluid is now 7.14 times 10 to the 6 less than the original pressure. So negative is perfectly fine. It just means you dropped pressure instead of gaining pressure. And there's nothing wrong with that. That can possibly happen. So there we go. There's a Bernoulli problem. Are there any questions about this particular problem? Let's look back at what we did. So we started with the problem, of course, and then we drew it out. Because usually if you draw a little picture and you label the picture with all the information, it's easier to pluck out the data to plug into your equation from a picture than it is from the text of a problem. So we had a pipe of a certain size, it goes up a certain distance and then constricts. So I drew that out. Plugged in all the information, give it in the problem, and then I say, okay, this is obviously a Bernoulli problem. What is it I'm looking for? I'm being asked to find the difference in pressure. So I rearrange Bernoulli to have difference in pressure equals blah, 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 whatever. I then say, are there any terms that I can cancel out immediately? How would I know? Again, if I have a change in the size of the pipe, then the velocity will change. If I don't have a change in the size of the pipe, velocity won't change, so I could cancel out velocities or the term with velocity in it. And same goes for height. If the height of the pipe doesn't change, then the terms that have height in it just cancel out. This particular problem has both, so I can't cancel anything. All right, well, there's Bernoulli. Plug all my numbers in, get an answer. The problem is one of the terms, I don't know one of the numbers, and that is, I don't know how fast the fluid is flowing in the second part of the pipe. Once I've constricted, the velocity has changed. So in order to do this, I first need to know, how did the velocity change? What's the new velocity? In order to do that, there's a separate calculation we have to do, which is the continuity equation. And so I leave Bernoulli to the side, and I calculate over here how to calculate the new velocity of the fluid. So I write down continuity. I'm looking for the second velocity, plug everything in. I know the sizes of the pipe, so I know the areas of the pipe, pi r squared, plug it in, get an answer, check the answer. Say, does it make sense? In this case, we constricted the pipe, so the velocity should have gone up. And indeed, that's what I found. So it's okay. Now I know the new velocity. That means I now know all the data to plug into this equation. And so that's what I do. I start with Bernoulli. I have all the terms sitting there, so I just plug my numbers in, making sure, of course, all the units are correct. I'm using meters everywhere. I'm using meters per second for the velocity, all that kind of stuff. Plug my numbers in and I get an answer. So any questions on Bernoulli's principle? All right, well, let's see. All right, let me introduce the next topic, which is still fluids, but kind of another type of calculation we can do. And this deals with the relationship between the pressure felt by an object and how deep that object goes into a fluid. So it's called the pressure versus depth relationship. So it turns out that when you have an object and you place the object in a fluid, the fluid will apply a pressure to the object. So imagine you sitting here or sitting there in your room or wherever it is you are. You're sitting in the atmosphere of the Earth. The atmosphere, air, is a fluid because it's a gas. And the fact that you're taking up space means the air had to move out of the way to make room for you, but it doesn't like doing that. It wants to go back where it was. So the air is pushing on you from all directions. The air is applying some force over your body, which means there's a pressure on your body. And of course, that pressure is called atmospheric pressure. So that one we could call P atmosphere, ATM, atmospheric pressure. And it happens to be a number. Here on Earth, at sea level, it's about 1.01 times 10 to the 5th pascals. Okay. Of course, if you go on a mountain, the pressure is going to drop. If you go underwater, the pressure increases. But we're just going to say everything's average. Every single object on the Earth feels atmospheric pressure, always, no matter what it's doing. It will always feel this pressure. Now, notice something, though. Let's say you're riding a bike and the bike tire is flat. So you go to pump up your bicycle tire. When you plug the bicycle pump into the tire, there's a little gauge that tells you how much pressure is inside the tire, because if you're going to fill up the tire with air, you need to know how much air to put in. And the way we know is by the pressure. The more air we put in, the more pressure there is, because you're filling up this tire with excess air. So it wants to be shot out, basically. And so as you fill up the tire, you increase the pressure inside the tire, obviously. And there are directions. If this is a bicycle tire, maybe it's 50 pounds per square inch or PSI. Or if it's a car tire, 32 or whatever it happens to be, we're told how much pressure should be in the tire. But when we first plug in the pump to a flat tire, the little gauge says there's zero pressure. But we know that's not true. Yes, the tire is flat, which means the tire is empty, but it's not truly empty. It just means that whatever air is inside the tire is just the natural atmosphere of air. It's not a vacuum. It's not like there's literally nothing inside of the tire. It's just not blown up. And so this brings to mind something quite important. The fact that everything on Earth feels atmospheric pressure all the time generally means we could just ignore the atmospheric pressure. Whenever we deal with something in the real world, we're always talking about how does the pressure change. When you blow up your bicycle tire, you don't care that when it's flat, there's some pressure there, 1.01 times 10 to the 5th. Who cares? What you care about is after it's flat, you then pump it up and you give it 50 psi more than when it was flat. The fact that there was already something in there when it was flat is meaningless to you. Or when you deal with a scuba diver who goes underwater, as you go deeper and deeper, the water pressure builds higher and higher until it becomes dangerous. In fact, as you go deeper and deeper, it'll crush you, which is why we have to build things like submarines, and even submarines get crushed as we go deeper and deeper. But a scuba diver doesn't care about the atmospheric pressure. Yes, he feels it the whole time, but that's just his normal state. That's like his zero level. And so this means that usually what's important is not the total pressure that an object feels, but rather how much extra pressure does it feel more than atmospheric. So this is what's called gauge pressure. Gauge pressure is the extra pressure something feels on top of atmospheric. And so what we could say, let's do it this way. There's three types of pressure we can think of: gauge pressure, atmospheric pressure, and something called absolute pressure or total pressure. Okay. And the relationship is the absolute pressure is atmospheric pressure, just the fact that you're here on Earth, you already feel a pressure, plus the extra due to whatever is going on, which is called the gauge pressure. Okay. So there's a little relationship. The total pressure an object feels is, number one, the fact that it's on Earth, it feels atmospheric pressure. Then, let's say this is a bicycle tire that you're blowing up with a pump. The total pressure felt by the tire is the atmospheric pressure plus how much you're blowing it up with the pump, the gauge pressure. Or a scuba diver diving underwater. How much pressure does he feel? Atmospheric pressure plus the extra amount of pressure because he's underwater. So the gauge pressure is only the extra bit. The absolute pressure is the total amount with the atmosphere. Okay. You need to understand the difference between these two and recognize when you're reading a question, which is being asked. Because given a problem on a test or the homework, you may be asked, what's the gauge pressure? Or how much pressure does a scuba diver feel as they dive 100 meters under the water? Or I can ask, what's the total pressure felt? And so the rule we're going to use, and this is purely my rule, this is not some standard of all of physics. The rule we're going to use in this class is anytime I ask you for the pressure, you automatically assume it's gauge pressure. Unless the problem specifically says, give me the absolute pressure or the total pressure. So if I give you a problem that asks you to calculate the pressure on an object because of whatever, just say he's asking me for gauge pressure. If I'm not asking for gauge pressure, then the problem would say something like, calculate the total pressure felt by blah, blah, blah. Or what is the absolute pressure on this object? Then you know it's the gauge pressure, plus you add atmospheric on top of that. Now, once we have this, the actual relationship we're going to discuss, I'll go ahead and give the equation now, and in next class we'll go over how does this come about. But the equation we're going to use is the pressure or the gauge pressure felt by an object, which is at some depth underneath the surface of a fluid, is given by rho, the density of the fluid. So what kind of water, what kind of fluid are you in, times G, 9.8, times H, where H we're calling the depth. Obviously, it's height, but when we talk about this, we're talking about how far down do you go rather than how far up. So rho is density of the fluid. G, of course, is 9.8, and H is the depth. The further down you go, the more pressure you're going to feel by the fluid. And then this is gauge pressure. Because if you think about it, if this is the equation and you're a scuba diver, and I ask, okay, well, if this is the equation, how much pressure do you feel before you even get into the water? Well, that would mean you're at a depth of 0. You haven't gotten in the water yet. And so this equation would tell you you're at 0 pressure. But you know you're not at 0 pressure. The atmosphere is pushing on you. So you should at least be at atmospheric pressure. So that tells you this equation does not take into account atmospheric pressure. So this is an equation about gauge pressure. The extra pressure an object feels because it's underwater, basically. All right. My voice is kind of giving out right now, so I'll go ahead and leave it there. Next class, we're going to get more into this. We're going to discuss the pressure-depth relationship. And then we're going to get into buoyant force. Buoyant force is that force which is the reason some objects float versus sink. You put an ice cube in a glass of water, it'll float. You put a rock in a glass of water, it'll sink. Why? Well, that's called the buoyant force, is what does that. And we'll discuss how it happens, how it comes up, what's the reasoning behind it, and then how to calculate it. All right, so that's all I have for today. If you have no questions, of course, you are free to go and enjoy the rest of your day, and I will see you on Tuesday.